There you go, Peter. That's exactly right. Yeah. So while we wait, I mean, anyone do experiments with the number of traces it takes to break AES on your chip whisperer? Did anybody do that experiment? What was your, I mean, if you don't mind sharing, what was the threshold? Were you, I mean, at some point no longer able to break it?
About 1,000 I needed.
You needed 1,000
Maybe
traces?
a little over.
Okay, but in the ballpark of 1,000.
But about 1,000, yeah.
Okay. Anybody else similar results, or anybody do, you know? Yeah. So now that it's 8 o'clock, I can at least say the punchline to today's lab will ultimately be we can break it in 50 traces. That's 50. So that's 20 times less than the minimum we were able to do. And not to upset anybody, but by the end, we'll be able to do it in 4 lines of code.
Whoa.
Yeah, you know, and that includes printing. So, all right, I'll likely repeat some of that here in a moment. Let me, yes, I'll message come through in the chat. No. Okay, so let's see, it's 8:01. I'll wait a few more moments for the people that are hopping on. But yeah, I'll just reiterate, if you could go ahead and download Lab 5 from either CoCalc or WILE courses, and then boot up your own instance of Jupyter Notebook / Chip Whisperer. That would be great. Let's see. All right. Okay. Let's get started. So, for those of you just joining, I was mentioning to the group that in last week's class we focused on breaking AES using differential power analysis. We split everything based off of 1 bit that was basically transitioning, and we were able to do it. And if you ran experiments, if that was the thing you decided to do for the homework portion, if you ran experiments on the number of traces required, things started to break down at about 1,000-ish, right, plus or minus, but in that ballpark. So for sure, I mean, you need 1,000 plus traces to break AES using differential power analysis. So we're going to leverage basically the correlation power analysis this time. We're going to go a step further. So in differential power analysis, we were looking at 1 bit. It was 0 or 1. In correlation power analysis, we're going to look at basically, we're going to start looking at those Hamming weights. We're going to look to see if we can relate the total number of bits that are on in a number to the power generated. So the sketch for today is 1, showing that there is potentially, we hope, otherwise none of this is going to work, a relationship between number of bits on in a value and a number and power. So that's going to be the first part of the lab. We're then going to use that knowledge. We're going to write a handful of helper functions to compute mean, standard deviation, covariance. So we're basically going to write a handful of functions. They're one-liners using NumPy. And then we're going to use those in performing a correlation power attack in conjunction with a Hamming weight model. After we do all of that work by hand, I'm going to show you that the chip whisperer / the functionality embedded within the the chip whisperer package allows us to do the same thing in like 3 lines of code. And then you're going to get really angry. You're going to be like, why are we spending all this time doing it by hand? Well, there are limits to what the chip whisperer knows. The chip whisperer is making some assumptions on the type of SBox, on the type of AES implementation, on a lot of things that you can also tune and you can reuse. But if you don't understand the process, it will make it really hard to ever pull off one of these types of attacks without having ever seen the attack itself. Right? I didn't want it to be this mysterious, like, oh, look, run .attack and it attacks a chip. To me, that's, I mean, while it's cool to see, that's not really beneficial for you. All right, so with that, hopefully that's given you enough time to download the lab and boot up your virtual machine or whatever environment you're using and upload this lab to Jupyter Courses UWYO Lab 5, right? The place that we've been working in recently. Fill out these details as usual. That would be good. These question marks, because it doesn't really matter for me. And we're going to run through the elements. So you should be able to communicate to your chip whisperer and set up your environment and program it. So none of that should change. But basically that first little bit should work out just fine. Right? And if you have issues there, more than likely it's making sure that you've actually uploaded it to the correct location. Right. And I guess just let me know when you've made it that far. That's just so we're all on the same page. So I know that I just finished saying that we're going to be able to break AES in 50 traces. Before we get there, we need to make sure that what we're about to do is legitimate, that there is a relationship between Hamming weight and power. So we're going to do a little bit of preliminary investigation to see if that relationship holds. So notice somebody has joined the wrong room. Okay. All right. So the very first thing is capturing 1,000 traces. I actually don't think there's anything for you to do in this cell. I'm pretty sure that I left it pretty blank. So this is the longest thing that we'll wait for this entire lecture, and that is the characterization phase. I mean, basically grabbing the data for the characterization phase. That's it. So we're grabbing 1,000 traces from our chip whisperer. So in theory, if you had these 1,000 traces saved off from a previous lab, you wouldn't even have to do this step. Since we've done it enough times, I'm not going to make you repeat what AES internal is. This should look very familiar, right? We have an SBox, and basically when we run the AES internal function, we're mixing some input data with a key through an XOR function, right? So this should not be a surprise as well, and the test should work just fine. This is, I mean, these are things now that we've done for, this will be the 3rd week in a row that we've done, and that's box and the AES internal. So hopefully nothing is broken there. Okay, now comes some fun stuff. We are going to be using the Hamming weight of a number. So if you run this cell right now, it actually will work. It's actually done. Like I didn't even give you many fun things to do, because this is a slow version. This is an uninteresting way in my mind to do a Hamming weight. Basically converting an integer into a binary string and counting the number of ones that's in line in cell 4. It works. right? It's yeah, it works just fine. I want you to double check that it works. So if you come down into cell 5 here, there's a handful of question marks. That's these, sorry. Sorry, I couldn't mute myself in time. I can't find the mute button. So notice in cell 5, there's a handful of these that have question marks. This is going to come down to your knowledge of how to convert these into basically how many bits are on. I'll give you some hints. Some of these are very easy, especially the last one here that's in binary. Right, there are literally 2 bits on in that number. And let's see, the number 3, how many bits are on in binary? So 2 bits that are on. Yeah, 2. Perfect. And then how about 0F? A little bit tricky. In hex.
4.
4. All right, let's try it out. See if we're right. And if we hit Shift Enter, you're right. So basically those numbers 8, 0, 4, 1, 2, 2, 3, 2. And I mean, you can go ahead and validate that. Basically, look, the Hamming weight computation here is super simple in the cell above it. Convert to a string, count the number of ones. That's literally what the Hamming weight is. We don't have time. I mean, we could, but we are going to be using Hamming weights everywhere. We actually don't have time to convert things to a string and then iterate through and count them. That's really, I mean, in terms of big O analysis, it's actually pretty expensive. I mean, it's not slow, but it's not efficient. So let's create a fast way to do this. The fast way, I mean, one fast way and punting way is to just create a lookup table. So that's actually what cell 6 does. So cell 6 is going to create a lookup table for Hamming weights. It's going to go through the 256 possible options, 0 to 255, and it's going to essentially add the Hamming weight to an array, and we're going to be able to quickly do this lookup. So it will work, and then I have this this random definition. You're going to say, why you have another definition for Hamming weight fast that just calls, that does a function call. Well, if you go for 4010 students, this is a bonus. For 5010 students, I'd like you to at least attempt this later. If you head over to this Wikipedia article, there's actually a nice listing of efficient ways to implement basically Hamming weight computation. So what you could do is you could replace this very, calling it a punt because essentially we're trading space, right, a lookup table for computational effort. And there is an interesting reason for that. But basically, the number of total times we have to compute the Hamming weight is actually less than the number of potential Hamming weights that we have. Not Hamming weights, but possible values we could be entering. So there are some reasons why you might want to define a function as opposed to a lookup table. Regardless, if you run this, you're going to generate that lookup table. And then, I mean, if you want to, you can just copy the numbers from above, or you can test out your skills and remember, recompute all of these. And make sure that the fast Hamming weight version works as expected. Now, I know we didn't do any timing information. You can put some timing checks if you want to see that that's slightly faster. It is, I mean, but from our perspective, that print statement probably takes longer than anything else. So, all right. So now what we'd like to actually see if maybe we can tell a difference. We have all these plots, we have 1,000 plots, and we have a way to compute Hamming weights. So why don't we attempt to plot out each trace, and let's color the trace based off of the Hamming weight of basically a value within within the actual computation. So a few things to do in here. On the for loop, we need to actually figure out how many times to iterate. So what are we iterating over? What is this that we put in the length here? I think I saw Peter mouth it. I think. Did I see you say trace array? Yeah, okay. Yeah, length of the trace array. And now you can torture yourself with what Hamming function you want to use here. You can either use the slow one or the fast one. Or if you really wanted to, you could rewrite this to just do an immediate lookup. So I'm going to, I spent the time creating a fast version, so I might as well use Hamming weight fast as my function here. So what should happen is I should be able to get the Hamming weight of, in this case, it's going to be the first byte being used and the text for each, basically each run of AES that we've done. So we're only attacking the very first byte of computation. So this mirrors a lot of what we did in the first, one of the first labs, where we just looked at a single byte and all across all the different. So one of the cool things, by the way, in this particular cell is we're introducing a brand new library. We don't actually have to, but I think it's Boca. I mean, I've used it when I was a data scientist down in Boulder quite a bit to generate things that ended up going into live web pages. So one of the really cool things about Boca is it allows interactivity and it allows you to do some really nice embedding into other sites and still maintain that, that functionality. So when we run this, it does take a little bit the very first time. We're going to, oh, leave it in there. Okay, yeah. So 1 of 9 colors, and unfortunately you're going to be disappointed, by the way. I apologize, because I don't know about you, but it's kind of hard to tell where the colors differ in there. Right? I mean, there's a lot of different colors. You can zoom in, right? So you got a whole bunch of nice zooming functionality on the right-hand side. So I don't know, I'm going to zoom in this segment here. And I mean, there are places where clearly it differs. Oh, I was pretty good there for that. You get really close. I mean, there are 9 individual colors in here related to different traces, but there's also 1,000 traces. Right. So there is, I mean, I see a lot of green, purples, grays, probably a blue in there, but there's a lot. This is, I mean, kind of cool, but I don't know about you. I really can't tell what's going on. Right. So what is the technique that we used in prior classes, prior labs, to try to identify differing information? What's the one trick that we use to start trying to isolate interesting things from a very noisy signal, from many different signals? Tried to read lips, but I also saw Michael posted subtracting a control trace out. Yes, so subtracting control trace, and then one of the other versions of that was subtracting out an average trace, right? So there's kind of a hint in the next cell here. Here is a set of Hamming weight traces, right? And I mean, there's likely a better way to do all this, but what we're going to do here is we are going to essentially, and by we are doing, a lot of this is in here. I didn't strip out a lot in this slide because there's quite a bit going on. We'll keep it.
The y-axis, okay.
Oh, go ahead, Gui.
I want to know the y-axis is the Hamming weight or other.
In this
the
graph,
scope.
the
Yes.
so the y-axis is actually power, and the color is the Hamming weight.
Oh, okay.
So so basically, so if I go up here, so up here we compute the Hamming weight for each, basically one trace at a time, we compute the Hamming weight. And what you'll notice is line color here at the end in the next statement. Line color equals color mapper, which is something we've defined up here. You can actually change this. If you want to look into Brewer, you can change the type of color pattern you use. But basically what this does is it creates 9 separate colors to choose from in color mapper. And down in the plot, we are doing a line equals color mapper. And then Hamming weight of byte is one of 9 values, 0 through 8. And so this color mapper will choose a specific color for each Hamming weight.
So it shows the percentage of the number of ones, right? Because Hamming weight denotes the number of ones. So in this figure, it denotes the percentage.
No, so in this figure, it is basically each trace. So there's 1,000 traces laid of one on top of another. So if we zoom in, let's go. Pick this up, we might be able to see something. So if we zoom in here, what's a little bit hard to tell, there are 1,000 traces being plotted in this, basically within this plot, there's 1,000 traces. And each trace takes one of 9 different colors. But statistically, if we go back to what we were talking about a couple of lectures ago, like there should be very few traces with a Hamming weight of 0 and very few traces with a Hamming weight of 8, because those statistically don't happen often. So the traces we see often should be the traces with, you know, basically, I mean, if we go back to the Pascal's triangle, right, we're going to see way more traces with basically 2, 3, and 4 bits on.
Mm-hmm. Oh, okay.
So that's why we see dominating colors of, I mean, in this case, we see really a domination of green quite a bit in here. So let's pull up a different Brewer set. So let me, just so that you can see some variation in color. So let me look up the, I don't have these memorized by any stretch. So that's not what I needed. All right. So I don't need a full one. Let's see if we're using Bokeh. So if we were to print out, by the way, the color palette, you would basically see probably some hex values here. So, but you can also define them, which is, so let's do something that is more drastic than, I think we're doing PRGN, I'm pretty sure that's the one we had. We could do something that deals more with scale. So we could do blues, for example. Let's see if blues is built in or not. So basically what this is doing is it's picking 9 blue colors, associating them in order from basically from 0 to 9 and sorting them. And we're gonna get, hopefully, a plot of all blues, which is gonna be harder to differentiate. Yeah, so in this case, in this diagram, the darker the blue, the closer to 0 Hamming weight it is. So if we zoom in here.
Oh, yeah.
But it's really tough to tell, right? I mean, so basically the whole point is, okay, we can see that there are different colors and there's variation, although I would argue in the blue scheme, it's really hard, but you can actually see in here, there's actually there's a handful that are really, really dark. I mean, again, this is a terrible like visual representation. It's kind of the point of like, we need to do something else. But then there's a couple that are really light, and then a lot of them are average in color. So color palettes are an interesting thing, by the way, in terms of, when you're representing data, finding one that is appropriate for your type of data is really important. So I would say the blue one, while it does show some things off, isn't very useful. You can look at other ones, right? So anything with scale is probably not very good for us, right? Because it's going to be really hard to differentiate different traces. We could try dark too. We could try paired. Paired might be nice. See if there's any. Set 1 looks like it's pretty varied. So let's try set 1 just for fun. So the capital S it should have been. Okay.
Cool.
So if we do set 1 here, perhaps we'll see something a little bit better. So while this is running, one last time, in our next step, what we're going to do is we're going to start computing the averages, the average for each trace, right, for each potential Hamming weight. So here, that's actually pretty good. I like that a lot. So here is now showing you that there are different colors for sure. There are 9 different colors in here. And if you wanted to, you could go try to compute. Okay, do all the yellow ones do the same thing? Do all the green ones do the same thing? Do all the purple ones do the same thing? And our goal is to see if there's somewhere within this larger trace, where there's a distinct difference between the Hamming weights, a relationship. I would argue it's really hard to tell from this, even though, I mean, we can tell that there's differences. So we're going to come down here and we're going to basically start bucketing our traces based off of their Hamming weight. So in the prior lab, we just bucketed based off of a single value. Remember we did the 0 set and the 1 set? Some thumbs up or some waves to remember the 0 and 1 sets that we bucketed traces into. Okay. Now we're going to bucket, I mean, we basically split our traces. That was the whole point. We did this split, a 2-way split. Now we're going to do essentially a 9-way split for things with Hamming weight 0, 1, 2, 3, 4, 5, 6, 7, and 8. So we have Hamming trace sets here, and we've got 9 of them. Right? We've got basically an array of 9 arrays, a list of 9 lists. So for each, basically for all the trace arrays, we first compute the Hamming weight, right? There's the computation of the Hamming weight, and then we're going to add, right? We're going to add the trace that we just computed the Hamming weight for, Hamming weight of byte. We're going to append the correct array, I mean, the correct location here, right? So if this happened to be 3, 0, 1, 2, the third one is where we're going to append that into, right? So in the end, what we should see is individual bucketing of all of these traces based off of their Hamming weight. We can compute the average for each one of those. So, again, trying not to like push you all over the edge immediately. We're computing across the entire array the average for each one of those. Ultimately, where we're going to end up with is we're going to be able to see an average trace for each one of these. So let's just see what happens here. Let's actually pick this nice color just so we get it again. That was set 1. So I'm going to change pastel set here to set 1. I know it's not pastels, but set 1 for the color board. And let's see what happens. What we should see, hopefully, is one area where there's divergence of the Hamming weight, the average Hamming weight trace from the average trace for each one. So here, let's see. All right. Okay, I know it's subtle. There's a lot of noise still there. But what do you see in the middle? Maybe that, maybe I should reset this. Let's do this to clean it up. So we're still seeing all the leftovers from the last set of traces, by the way. So if you want to clean it up a little bit, we can do a new figure. I mean, if you don't want to lose your last one, change the figure to G. Doesn't matter. Change it to some other letter, and we can do it this way. So I basically, all I've done is I've reset it, and now this is pretty clear. Right now I'm seeing all the traces from before. But now if we zoom in here, we should see one instance in time. I mean, there's a couple, right? But there's one instance where there seems to be a very dramatic set of differences. Sorry, my ability to. So this is what, around 538-ish. There's, I mean, when I subtract out the average, I tend to see now 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 unique traces, right? 9 unique, basically, power consumptions. And the colors are completely different, right? That's 1 per Hamming weight. You need to see that a different way. The first thing is visual inspection is terrible. I've ever mentioned that before. I've mentioned it in a couple of classes. Visual inspection works to see things, but really from a repeatability standpoint, it's terrible. So we could find the location within our set that has essentially the biggest difference between the average trace and the average per Hamming weight. So that's basically what we looked at here, the Hamming weight average, subtracting out the overall average. And we get that at location 538, which visually we also found. Now, there is a little gotcha here. Again, we're still seeing it visually. We should probably validate that what we're observing is going to be useful. So this next cell plots that it plots. Wow, and I actually did one additional thing for us that's not in the normal one. I'm going to see if I can zoom this out a little bit for you. Okay. What do you see there? This tweet, by the way, might be what you were looking for earlier in terms of result. So we have our Hamming weight along the X, and along the Y, we have basically the power measurement. So the question that I would ask all of you is, what relationship here, what feature is going to enable us to actually do correlation power analysis? What is the one requirement to do correlation analysis that I mentioned? What assumption do we make if we can do correlation?
Linear relationship?
Linear relationship. If we don't have a linear relationship, correlation power, or correlation analysis in general won't work. Okay. All right. So now the fun part, right? We basically, this whole thing was to prove out that there is, oh, yours is flat between most of the values except the first one and the last one. Really? Okay, just for fun, can you remove the scatter plot version? So there's a scatter plot line in here. There might be a data point or two that are off, by the way. So that's, so if you comment out the scatter plot and just do the line plot, you get anything that looks a little bit better, and it shouldn't make a huge difference, but you might. For those of you that are having, is your ship whisperer working correctly? No. Okay. No. So what you can try to do, if you go back to the data collection. Okay, so some of you are getting linear correlation. How many of you are getting linear correlation? And if you can do the reaction of, I don't know if you've got the option between yes and no on your reactions, that'd be super helpful. Or a thumbs up works for me. I can understand thumbs up. You can use the surprised face for no if you don't have an X. All right, let me look. Andrew, I'm looking at yours right now that you posted.
Mine is what's a linear correlation.
Okay.
Oh, it depends on the physical machine. If you don't get this relation, I don't know.
Yep. So Michael posted out that recapturing more traces again, and it worked. So again, remember, we are. Oh, that's fun. Sorry if anybody's looking at what Andrew posted in the chat for his. Andrew, what happens if you do collect, let's say, 2,000 traces and run it again? So there's a handful of things, by the way, that I should warn everybody about. Right, we're playing with a chip whisperer that is an open air device, and it can be around other things. We're doing sensitive measurements. If you are close by, and you're touching it, or it's touching something, the measurements could be way off. Right? I mean, again, this is a sensitive piece of hardware that is collecting data. So it is susceptible to interference, right? Especially on the scales of power that we're measuring. So this is going to sound crazy. Blow on it, clear it off of dust, make sure it's not touching anything else. Make sure it's not sitting by something that's noisy. Don't run your microwave at the same time that you're operating it. Okay, some of those are a little bit funny, but let's see, Andrew, what your second one is here. Okay. All right. So, Andrew, the one thing that can I ask you to do is before the for loop, before the for Hamming weight in range 9 in your code, can you put somewhere in there key equals figure, open close parenthesis, just to reset the trace itself? Because it actually looks like, I'm actually much happier with that second one. I think you're actually good. I think that first set of data is actually incredibly noisy and has a really low voltage compared to the average. So that's actually, that's a good start. So you're good. I think you're good. Just the line I'm talking about doing, Andrew, is this one right here that I'm highlighting. Instead of G equals figure, though, based off of your code, you're going to do P equals figure, and that's basically going to reset the figure to get rid of the huge amount of noise that's at the bottom. But I think you're going to be okay. And that's going to be in cell 7. Let's see, cell 9. And Danny, yes, it's like a Nintendo cartridge. Blow dust in it. That's right. It makes you makes everything work again. Okay. All right, so did everybody else, okay, look, Andrew, it looks like that works, perfect. So everybody's seeing something like this if they zoom in, right, to some extent. And then as you go down, you get somewhat of a linear thing. It's not going to be perfect. Again, we're talking about pretty, there's also some amount of randomness. Tanner, what does yours look like? And for those of you that had other things that didn't look like this, yeah. So Danny, try rerunning cell 3. Again, it could just be a data collection issue. So basically set the chip list for maybe in a new location, flip it over. I don't know, do all the things that shouldn't make a difference. Make sure there's not a cable running on top of it. Make sure it's not looped under the USB cable, right? The USB cable is sending data. And so if you're sending data over a USB cable and you're trying to measure power, you can get some interference there. So yeah, so rerun the capture, trying to place the chip whisper in a very safe spot. So one of the things is when we're dealing with 5,000 traces or more, it's kind of a little bit, it's less likely to get some noise that would interfere, but we're capturing fewer and fewer traces. So let's see. All right. And Tanner, if you could let us know what happens when you try to rerun it. Yeah, that's, so yeah, so what this looks like is that the 0 is just way off. The other ones are actually probably okay. It's just that your 0, 1 is way, way off from a Hamming weight perspective. So the rest looks linear. I mean, ish. I mean, I know it's not perfect, but within the large scheme of things, it's pretty good. That and 6 is a little low. Yeah, I mean, it's yeah, okay. So yeah, you can try to experiment, but this whole point of this part of the lecture is just to show that there is a relationship. So now we're going to get to maybe more fun. And we're going to only capture 50 traces. Yeah, Tanner, I would just keep the one you have for now. Because it's basically what we've done in the past isn't going to influence these future traces. So we're only going to capture 50. So that's pretty quick. It only takes about a second or two. All right. So again, when you're capturing this data, I mean, even if you want to hold your USB, your chip whisper up in the air somewhere. And we are going to, yes, Shay, we are going to do a Pearson's correlation here in a few moments, actually. So rerun it, capture 50 traces. And then because, just to make sure you've only captured 50, you're not cheating. We're going to validate that. And now just to make sure that we have it, let's plot it. I mean, this shouldn't be any new thing. So let's look at trace array, and I ask for the 40-second one, and I ask you to do it in green. We have a trace, spectacular. And now comes maybe some fun part. So I basically took this from the lab that was generated by the Chip Whisper people. They want us to do these by hand, which is not so much fun, but it's not terrible. All right, this is basically testing your NumPy skills. And I've given you a little bit of some hints here in the actual code base below. So we are looking to implement 3 functions: mean, standard deviation, and covariance, right? So I guess the question would be, how can we compute the mean of X? I mean, there's some really easy ways that probably don't require this much work either. But any suggestions on computing the mean? I'll read the chat.
Yeah, NP dot mean X.
That would be a lot easier than all of this. Yeah, so if you look at the at the suggestion from the author, they want you to divide by the length and do a whole bunch of other things. So let's see if this works. Let's do NP. Let's take Lee's suggestion of doing NP mean.x instead of, so by the way, the author of this expects you to implement it doesn't even matter. Yeah. Oh yeah. Yeah, they were expecting us to do np.sum and then dividing by the length. But I agree, np.mean seems like it'd be a lot quicker. So I'm okay with that. All right, for standard deviation, they want you to actually test out that you understand how to do this, but I agree that this might be a little bit much. So the standard deviation is basically, it's a summation of a square, I mean, basically a square root of a summation. So you could do, I mean, just to test out your skills in NumPy, np.square root, right? And then internally, an np.sum of what? Well, of x minus x bar squared, right? So to do that, would be one option. Covariance with sum again, based off of the crazy formula that I see above. If you look at covariance up here, the sum of basically y minus y bar times x minus x bar. And again, if you're seeing inefficiencies here, and these are the authors of Chip Whisperer, there are some potentials for you to contribute to the open source community. Especially if you're currently looking for a, say, a job. Oh no. Aha. So, and this is why they probably didn't want us to use mean. Right. So if we go back to sum, they want us to actually be able to do this in a first space that is potentially not just an array. So I did go ahead and update the mean one, which should have worked, but because of the data that we're passing in, it's possible that we need to handle different types of data. So the axis equals 0 here is going to let us do it on a per row basis, essentially. So I think we could probably get away, by the way, for those of you curious, I think we should be able to do np.mean x, this equals 0 should have also worked. Let's see if that's right. Yep. So if you want to do this in a realistic way, oh my goodness, there we go. There is a one-liner. The one-liner is using mean and setting the axis equal to 0 so that you force it to stay within one row and not do the mean of the entire data set. All right. So does everybody have roughly this? I mean, so the first one is computing the mean, which you can do directly, or if you want to prove to yourself that it's summing up over the length of an array or a set and dividing by that length, that should work equally well. Standard deviation, same thing. By the way, we could have probably right, from the one-liner. Maybe. Let's see if that still works. So these should return the exact same thing. Oh, why won't that work? So I'm going to investigate why that's not the case, unless, oh, is it returning? That should have worked. Okay, well, I'm going to investigate what the MP version is doing, but that should have worked as well. All right, I'm going to move on because that craziness. Well, somebody could see it right away. All right. Okay, we can still, if we look at all the traces that ChipWhisperer captures, we get an array of arrays. So we get basically a giant matrix of everything that happens. We can compute the correlation using essentially it's the covariance function that we have. And all we need to do here is input our Hamming weight computation. We want to basically apply our Hamming weight across all of the internal guesses and text that we have. So we're basically creating a massive matrix of all the Hamming weights, and we're doing it for each key guess. So Hamming weight fast in here, we're doing it many, many times. Again, passing it in as a function, make sure. So what we should get is, oh boy, not a syntax error. Oh, how many potential keys are there? So we're doing 16 rounds, and in each round, how many potential key values are there for AES? Not a trick question. $256 possible keys. So we need to run through all possible keys and see which one has the highest correlation. I messed up this time. Maybe I need this bigger to see. Okay, sorry. There is a missing parenthesis. So we're creating an array, okay? Creating an array of Hamming weight of the internal trace. So there needs to be an ending parenthesis before, basically 2 ending parentheses before the 4. And that's actually the only change that should happen. So you've got, the whole thing should be wrapped So this is an array of arrays. You should have two open square brackets, two ending square brackets. And internal to that, make sure that your Hamming weight function takes in as a parameter AES internal, which also is a function. So does this work for everybody? I know that I think what was missing from the code was this ending parenthesis. I mean, in addition to adding in Hamming weight. Right. So if you could let me know when that actually works. So what we're basically, oh, where's that showing up, Addison? Where assert error in lines number 17. Oh, so if you're getting an assert error in 17, make sure that this is that your implementation of mean and standard deviation are okay. Let me see the chat here real quick. Okay, and Addison, line 8, return NP square root NP sum. Oh, yes. So the Addison, the power function is actually double asterisk instead of the caret. Yep. So that's a good catch. All right. So I know that there's a lot of hand waving for this one. Okay. What we're doing here is instead of just splitting based off of one bit, we're now using the fact that there is a linear relationship. And we're basically saying, okay, if I see this power consumption, what is the likelihood that it is this particular Hamming weight, or right? So basically, we're finding a way to do that relationship instead of just, is it a 0 or a 1? I guess the thing is that, okay, that's one byte, right? We've been able to do that many times, but now we're doing it with only 50 traces. Let's see if we can do this now as we did last time for everything all at once, for all of the rounds. So when we go to cell 19, we are basically going to do this 16 times, right? So the whole way through here, you should say 16 for the number of essentially our guesses for the correlate, I mean, basically what our correlations are going to be each time, and our guesses. When we run through this, we're going to run again through our 256 keys. And we need to, again, this doesn't change from what we had before. We compute our Hamming weight fast, right? And let's not make the same mistake as before. That should definitely end with a second parenthesis. So it's 2 parentheses to end that. So in this line, so that's right after the for loop that runs 256 times, your function needs an open and close parentheses to wrap that AES internal function, okay? And so what we should do now is, now instead of, like I said before, we're no longer splitting on 0, 1, we are doing, basically we're finding which key has the highest correlation, meaning that when we run through all of our text, the Hamming weights line up to the power consumed, basically the most times. We run this, take a little bit longer, but you're going to see roughly 10 seconds for us to break, maybe a little bit longer, 12 seconds. 12 seconds to break AES. last lecture, you were probably spending 12 minutes every time you did a new experiment. And we literally broke AES in 12, let's say 13 seconds, if you include the time it took us to capture. Best guess is 2B, 2B, 2B. So that's good. So Michael, were you actually able to get that linear relationship before or not? Or Peter, where you got the linear relationship, but then it, interesting. When you are looking at your, did you use 16 bytes worth of data that we're going to capture here?
Yeah, I did.
Okay. Interesting. Did anybody, so who else got that 2B, 2B, 2B? Anybody else get that result? Or something similar, that maybe not 2B, but some other?
I got to be, but the other parts are different.
Okay, so did you get, so actually if you run the very next cell to check, does it come out correctly for you, Hui, in line 20? Or cell 20? Yeah, so the thing you can do is, again, this is one of our limitations of the chip whisper, and again, I'm not going to take points off for this. We are dealing with a very sensitive, tiny little device, right? I mean, the difference between the chip whisper nano and the commercial version is about 100 times different price point. Okay, so the $50 chip whisper, it has potentially some issues. Try recapturing your traces, right? So try going back and recapturing. Basically line, if you go back to cell 13, try rerunning it from there and going down. And if that still doesn't work, this is going to be the ending part of this lab here in a moment. Go down to cell 21 and run cell 21 and I mean, just for the interest of time, 21, 23, 24, 25, 26, 27. So basically run the last couple of cells. And what's missing, by the way, in order for all that to work, so let's just run through it. For those of you that don't have the correct result, let's go through this and see if maybe there's a logic error. The way we're going to do that is we're going to leverage the internal tools of Chip Whisperer to see if we get the right result. So let's start in cell 21. We're going to recollect some traces, 50 of them, and we're going to collect them in, we're going to, for the first time, create a project. Oh, scope Chip Whisperer Nano is not connected. Connect it first. Yeah, unplug, unplug that thing. Let's see. So when you tried to rerun, cell,
Cell 13 is where I got the error. Yeah.
yes, yes. So I'm very sorry. The reason why you got that error is because we disconnected the scope and target at the end. So sorry, I wasn't expecting you have to rerun that cell. You can rerun cells 1, 2,
3.
and 3. Yeah, so rerun these first couple cells here. And actually also this last one. So rerun, and it shouldn't make a huge difference, but yeah, rerun at least these first 2 cells where it sets the scope type and the communication one. Right. I was trying to be fancy with the disconnect and I shouldn't have disconnected it yet. I'm very sorry, everyone. Very sorry. So disconnect is great when you're done using it, not when we are still in the middle of the lab. But now you know. So let me do that as well. That's a good gotcha. All right. So I'll point out the lines just for full, especially for those that are watching this video later. Right here in cell 13, we do a scope disconnect. Yeah, and so there's going to be some minor variations. You could try pushing it to 50, from 50 to 100 and see if that works for you, but 50 is like one of the lower limits of everything working. Let's see your comment there. Same error for cell 21. Yeah, so if you rerun cells 1 and 2 in the notebook, you should be able to now get back to remove the disconnects for now. I mean they're cool and all, except for so yeah, you can comment out the scope disconnects. It's not a problem. I mean, it won't hurt anything except that it will keep your chip whisper on. So if you ever try to, I mean, have 2 or 3 notebooks open at once, you're going to do different things. You might get into some issues, but yeah. So what's really cool about this one is we are for the first time creating a project. The project is going to start containing all the files that we've been handling ourselves in our separate arrays. Right? We've been keeping track of all these arrays ourselves. Huh, that's super weird, Peter. We'll figure it out. I'm not worried. So in cell 21, we create a project called, in this case, very creatively, proj. Might want to use more descriptive things. And we're basically appending our traces within there. So this looks a little bit cleaner than our previous versions. Yep, so we're capturing all that in here. We can see them all. So if we come here and we, for traces in project.trace, let's go to a dot, not a comma. And down here in the waves, we can do the same thing. We can do it for individual things. Need some semicolons. Actually, oh,
Yes.
thank you. Thank you so much, Lee. There we
You're
go.
welcome.
So yeah, there you go. You can see all the data is captured in I mean, all in one basically encapsulated space. You can do it for individual components as well. Yep, so Connor says third time it worked out well. Again, it could be just data collection is being noisy. All right, so now let's just validate that we can actually do this. We've captured some data, 50 traces. We're using a project functionality that Chip Whisper comes with. We're going to import the analyzer. And we spent all this time in the past creating our own models. There's some built in. So if you just do leakage models, and there's question marks right now, if we hit tab, you can see a handful of models that are built into the Chip Whisper platform. There are some that deal with Xboxes. Maybe we should try the Xbox outputs. That's what we've been doing this whole time, and see what happens. So we define a leakage model, and an attack in this Chip Whisper analyzer setup takes in a project, basically a set of all of the traces and texts, and it takes in a leakage model. You can print out all the parameters that the Chip Whisper is going to use by default. And in cell 27, you can basically do all the things from all of the cells beforehand and hopefully get the right key printed out. Now, if this doesn't work, then there might be a slight issue with the Chip Whisperer, right? If it does work, congratulations. We will then try to investigate what's going on with your specific code. So I know this was a very different kind of lab in terms of I didn't have to do a lot of manipulation. There is quite a bit going on. Recreating correlation analysis from scratch is not really fun. So if it's not working here, okay. Yeah, so we could try to investigate why the same key is being repeated over and over again. My guess is somewhere within one of the for loops. I mean, you can always try again now that you've captured new data to see if the upper one works. but yeah, we can look at individual code. You can either get in touch with me or we can try to isolate it. It could be just a fluke of data collection.
Can I see cell 21, please?
Sure can.
Oh, wait, sorry, 22. 22.
Yep, so dot traces
Waves. Okay.
and waves, yep. And by the way, you can do other things too, right? So if you get rid of any one of these and hit tab, you'll see all the different things you can extract out of the project it's storing. And again, there's a lot of information about the API, about the individual package on their website. I mean, but there's it can be pretty powerful. And you can also start saving things in new places. You can start building up traces over time. You can add to projects. So if you're getting low correlations, those are in the 60s. Yeah, so that's a little low. So there might just be some issues either in noise during capture. Yeah, that's probably the issue. So yeah, if things are working correctly in your chip whisperer and it's in a, let's say, a quote unquote quiet environment, it should be somewhere in the 70s to 80s for correlations if you are using the correct leakage model. So if you switch this leakage model from SBox output to something else, there's no guarantee. I mean, model matters. So I'm going to pick something at random here. I know isn't right. And I should, one, not get the right key and get some close to, yeah. And I get some great correlation, but clearly not all of that. So model matters. Being able to get that linear relationship matters. Without that linear relationship, nothing else will work. And again, some reasons for that might be, you know, the chip whisperers acting up. There's some noise in the environment. You know, perhaps the chip whisperer has a fault in it, right? I mean, you could try resetting it, unplugging it, letting it sit, plugging it back in. No guarantee that that's going to fix it. Clearly, you could try reprogramming it, right? The first couple steps. Perhaps, you know, something went awry. Doubt it. Maybe it's running hot. Maybe, again, most likely there's noise around the environment, right? How close is it to your PC at the moment? You know, extend it out as far as it goes and make sure that it's not by a monitor. When we're talking about 50 traces, right? When we're talking about 50 tiny traces, any noise is going to be significantly impactful. So it's being able to find relationships. So get the same error at cell 21. Okay, good. Rerunning the first 5 or so cells fixed. Yeah. So yeah, the big issue for those of you either that are going to revisit this lab later or take a look, make sure to comment out the target disconnect code in these cells. Unless you want to repeat, go back up and reconnect. But the disconnect literally stops the connection between the chip whisperer and the yeah, stops that connection. All right. So thoughts? I mean, I know it's not perfect, but I mean, thoughts in terms of power, in terms of where we can go with, I mean, how quickly by the end we can leverage the tools to do a lot of the manual work, a lot of the work that we try to do by hand. All right. Okay. Well, I mean, again, not a huge number of things, quote unquote, to do. And I, by the way, I'm not going to be taking off points, especially if you do the correct leakage model at the end here, and you aren't getting the right results. So if you actually do the SBox here, it's a pretty easy way for us to determine whether or not your chip whisperer is acting correctly or not, right? Because literally there's no implementation issues that should be happening here, right? I mean, it's all prepackaged. So yeah, you know, if you get to this stage where you get an output, I'm happy, all right? And we can, if you want me to, we can try to dig in. If you think that there's some issue on your side, right? If you're like, hey, I think there's a bug on my end, you know, I don't mind trying to help you debug it. Okay. I might even post this one. Might wait a day or two, but I will post this this process out for everyone to use as a guide. Right, if you want to double check your code. In theory, yes, the key should match that. 2B, 7E, 15, 16, 28, AE, D2, A6, 93, F7, 15, 88, 09, CF, 4F, 3C. Yeah, so couple of yours might be off. Again, if we go all the way back up to the picture of, so it's going to depend on how linear you're able to get, right? And I know that you have no real control over this. This is a measurement issue. But yeah, that's the biggest factor here is if you don't have a linear relationship, correlation becomes incredibly hard. And you might actually relate one data point to another one that's not supposed to. Yeah, so you shouldn't have to run 50,000 times, right? The whole point is we can do it with 50 in theory, right? If you're doing 50,000, I mean, it should be better. But at the same time, like the whole point here is that we should be able to do it with many fewer traces if we have a linear relationship, right? If you don't see this, right? If in, let's see, that's what, cell 9. When you do cell 9, you don't end up seeing a stark difference between your different Hamming weights. You don't have clearly identifiable traces for different, I mean, again, we don't know which Hamming weight is which here. The whole point is that doesn't matter. We just see that there's separation between them, right? You don't see that, then there's really no hope for anything else beyond that to work. And what that leads me to believe is there's a measurement issue somewhere, either noise or, I mean, or the chip whisper, like I said, is in a weird state. For kicks, you can always try rerunning last week's lab and seeing if you get correct results out of that. Yeah. So again, we're not taking off points. I know this is a really sensitive piece of electronic equipment. I'm not judging you on data capture here, right? It's the process that matters. So, all right, we are out of time. But yeah, hopefully this was still kind of cool. I know not as much work to do, but running through it. Focus on the end where we can start packaging everything up, leveraging your tools to handle a lot of the infrastructure. So, all right, have a wonderful weekend. Don't stress, as always, all right? And reach out to me if you want me to try to look at your code if you think there's something wrong with it. But otherwise, yeah, enjoy your weekend, all right? For everything.
Thank you.
Good thing.
Thanks. Have a good weekend.
Thanks, you too.